Now suppose the condenser operates as a total condenser at 40 degrees Celsius and the production rate of the overhead product is 75 kilomoles per hour. Okay, and the mole ratio of the reflux to the overhead product is 1.5 to 1. Calculate the molar flow rates and compositions of the reflux stream and the vapor feed to the condenser. So we'll look at the question one by one. So we have the overhead stream to have 75 kilomoles per hour, and the ratio of the overhead to the ratio of the reflux to the overhead. Okay, the reflux, which is the bottom here, and the overhead product B is 1.5 to 1, which is 1.5. So simply substitute V into here and we can calculate R is actually 112.5 kilomoles per hour. Okay, so to find what is F, we can perform total balance. So in equals to out, and you have your F to be 75 plus 112.5, and that gives you 187.5 kilomoles per hour of F coming into the condenser. And the compositions in the feed and the product stream are identical, which is 0.96 kilomole of butane per kilomole. So this is the mole fraction of butane in both the product and the feed stream. Okay, quite simple and straightforward. Now look at part C. Suppose now that a partial condenser is used. Okay, so not all the vapor is converted to is condensed to liquid phase. So with the reflux and overhead product in equilibrium at 40 degrees Celsius, and the overhead product flow rate and the reflux to overhead product ratio having the values given in part B. So the reflux to overhead product ratio is also 1.5 to 1. Calculate the operating pressure of the condenser, okay, and the compositions of the reflux and vapor feed to the condenser. Now, so to calculate R and F, it is the same as in part B because we have the ratio unchanged. Okay, so it is the same answer. Now, at equilibrium, we can use the Raoult's law again. So, Y, the vapor pressure of butane in this case. So we have butane and pentane. So the mole fraction of butane in vapor phase multiplied by P is equal to the mole fraction of butane in liquid phase multiplied by its vapor pressure, which we have calculated in part A using the Antoine equation. Okay, so this is your vapor pressure. Okay, vapor pressure of your butane that was calculated using Antoine equation. So we have two unknowns here. No, it's okay. We can use the Raoult's law for your pentane also. So you have 0.04 of mole fraction of pentane in vapor phase multiplied by P, which equals to the mole fraction of pentane in liquid phase. Now this is actually 1 minus x1, okay, because there are only two components. This is a whole number multiplied by the pentane's vapor pressure, which we have calculated from Antoine equation in part A. Now you have two equations over here, and we can perform simultaneous equation to solve for P and x1. Now to solve for XO, we can use the butane balance, the species balance, and F multiplied by XO is equals to V multiplied by the mole fraction of butane in the overhead stream plus R, your reflux stream, multiplied by your butane in the reflux stream, okay, which we have found here. So substitute the values in, okay, 112, this one we have found here, okay, R multiplied by 0.8803, which we have found here, x1 plus 0.96, okay, here, multiplied by 75, which is V, your overhead product, and that gives us XO to be 0.9122 moles of butane per mole of reflux.